Welcome. In this session in linear data analysis, we'll explore some guidelines for how to approximate a matrix. One way that we often do this is we explore the singular values. So suppose that A has a singular value decomposition that is of this form, and what we do is we form a sigma vector, which is the singular values up until their rank. And when we look at these may not be informative. So there are a number of ways that we can rescale this. So we want to rescale sigma I so that it's in an interval between 0 and 1. And this is a typical thing. So there are two widely accepted ways. One is to use the explained variance. And the explained variance will use the symbol theta, and that is the sum of the singular values. So that's from I going from 1 to our rank R of the singular values. And if we want to use vector norms, we could say that that is the L1 norm of the singular values. Another way is to use the total variance. And the total variance is often represented with a capital T, and that is closely related. It's the sum, as I go from 1 to rank R, of we take each of the singular values and square it. And that, we can see, is like taking this vector of singular values, and that's the squared L2 or Euclidean norm. What we then do is we plot the sigma vector rescaled by the explained variance, or we plot the sigma vector rescaled by the total variance. And in either case, what we get is something like this. Here we have the index I, and here we have sigma I divided by, let's say we divide it by theta. So what this will look like is this will be 0, and this will be a value 1. And unless this is a rank 1 approximation, we know that when we divide this by, let's say we divide it by all the numbers in there, so we're using theta, that we know that that is certainly greater than 0, and it's certainly less than 1, so it'll be some value here. And as we do this, what we'll often see is a picture like this. Is that this is called a scree plot. And it's called a scree plot because the person who invented this term was thinking of, if you think of how rocks fall down a mountain, what will happen is they'll fall down a steep part of the mountain, and then they'll stop falling, and they'll produce a pile of rubble, and that rubble is called scree. So he called it a scree plot, and what we're looking for in a scree plot is what's called the elbow. And if we plot the singular values of a matrix, and after rescaling, and we find an elbow in it, then that is a really good choice for where to cut this off. So this will be some value k, and what the scree plot tells us is if we use the value k, that is a pretty good approximation to the rank of A, and it's also, incidentally, a dimension k, or kd, approximation to the column space of the matrix A. So let's switch to some automatically generated examples that we can go through. let's explore some values. Here, I've set MATLAB's random number generator to a default value, and I've randomly generated a matrix that's 3 by 3 and has a maximum value of 5. When I compute the singular values of this, what I get are approximately 10.5, 4, and 0.5. So to a very rough guess, the sum of these is a little over 16. And what that suggests is that I could either have a rank 1 approximation to the matrix or a rank 2 approximation to the matrix, and going for a full rank approximation probably isn't really needed. Well, let's do some computations. When I work this out, what I get is that the rank 1 approximation is this, and the first entry is 4.7, so that's only 0.3 off of this. This is 4.6 is 0.4. This is, that's a factor of 2 off. That's not so good, is it? 4.26 is pretty close. 4.18, that's pretty close. 2.13, that doesn't look very satisfactory. And 3 compared to 2 isn't very good. 3.3 compared to 3 is pretty good. And 1.68 compared to 5, that's not a very good approximation. So I personally wouldn't be particularly satisfied by a rank 1 approximation to this matrix. But a rank 2 approximation based on these values looks like it might be pretty good. So when I add C1, which is the rank 1 approximation coming out of the SVD of A, and then I add C2, which also comes out of the SVD, this is what I get. The first entry is 5.2, so that's quite close. 4.73, 1.07. These are pretty close. 4.75, 4.29, 0.92, also within about 8%, right? And then the second column to 2 digits, the third column to 2 digits of precision equals my original A. So I would say, if I was looking at this, that a rank 2 approximation to A is pretty good. Now, what implication does that have? Well, if a rank 2 approximation to A is pretty good, then that means that A is approximately has a 2D column space. And those two things are closely tied together. What rank of approximation is good for the matrix, and what dimension approximation is good for the column space? Those are one and the same. Now, suppose I reset MATLAB's random number generator, and now I generate a 20 by 20 matrix with a maximum value of 200. I'm not going to print that out, and I'm not going to go through it. Instead, what I'll do is, so this is the statement that I used after setting the random number generator, and this is the scree plot. So what this scree plot is telling me is that if I have a rank 2 approximation, let's look at the numbers over here. This is 0.35. So the first singular value is capturing, let's say 33%. And then the second singular value is capturing, this total is about 0.8. So what that says is that if I use a rank 2 approximation to this randomly generated matrix, I captured about 92% of the total variance that's in that matrix. So this scree plot tells me there's a strong elbow in this random matrix, and after that, after this sharp drop off, this is the elbow of the plot, and after that, all we have is scree going down. We just have a bunch of rubble, which is the random variations that we get when we randomly generate an integer matrix. So what have we learned in this lecture? Well, we now know how to find the norm of a matrix. The L2 norm is what we get in MATLAB if we type norm parenthesis A parenthesis, and we can also ask MATLAB to give us the Frobenius norm. We know how to approximate a vector space with one vector. We know how to approximate a vector space with k vectors, and that's by approximating the matrix with a rank k approximation. And along with that, you can think about how we're able to approximate the null space of a matrix.